Thank you, Carrie, for the introduction. So Tom and I will be presenting the AQ&U instrument, and this work is still in progress, but the ultimate goal is to provide this instrument that can be deployed everywhere else where air quality matters. So this instrument would not be possible without this great team of professors, graduates, and undergraduate students. So our team members together, they cover multiple disciplines such as electrical engineering, chemical engineering, and computer science. But more importantly, it is the expertise that this team brings together. For example, we have expertise in sensor development, wireless networks, air quality measurements, modeling, visualization, and more. So one of the most prominent actors that provides air quality sensors in the Salt Lake Valley is Purple Air, and they manage to get out lots and lots of sensors. And KSL, for example, they use Purple Air sensor data to visualize air quality index. However, low-cost sensors, they are less accurate than, for example, sensors from the Department of Air Quality. So when providing visualizations that combine different sensor networks of different accuracy, the result is something like this here, where the creator of the visualization has to add a disclaimer saying, the air quality index shown here are from a wide variety of sensors, each with their own strengths and weaknesses. KSL is not responsible for inaccurate information. So unfortunately, citizens looking at such visualization do not know the accuracy of the sensors because neither strengths or weaknesses are visually articulated in the visualizations. So this is what we have. On the other hand, we have the Goldstar measurements from the Department of Air Quality, where DAQ has only a very limited set of sensors distributed in the Salt Lake Valley. And these sensors are highly accurate, but are very expensive and have a low time resolution. For example, for Salt Lake City, there are only 2 of these sensors. So this visualization here is of an inversion day in early 2017, and what you can see is a red blob over a significant part of the valley, almost up to Wyoming. This visualization does not take into account elevation, such as the Wasatch Mountains in the east, known local sources of bad air quality, such as refineries, and traffic on the freeways is not really appropriately covered through the provided measurements. So the underlying data of such visualizations does not have the spatial resolution to provide an accurate description of air quality. So this here shows air quality along the public transportation tracks in Salt Lake City. And we see that elevation differences causes air pollution gradients, and that local sources of bad air can lead to dramatic differences in pollution levels. So this provides evidence that we need higher spatial and temporal resolution data. So this leads us to our wish list. What do we need to get an accurate description of air quality in a location such as the Salt Lake Valley? So we want a higher resolution of air quality measurements in space and time. Purple Air already did the first step. We also want high quality measurements, but if the accuracy is lower, we need to be able to communicate that loss of accuracy and what it means. Sensors should be low cost because this will be one of the main driving factors for enabling a spatial dense network of sensors that measure air quality. And finally, we would like this instrument to be easily transferable to any other location. So to cover this wish list, we propose the AQ&U instrument, which provides low-cost AQ monitors. And these monitors store their data in our databases at the University of Utah, and we plan to store sensor data from any other sensor network that implements our interface. So we already pulled DAQ data and Purple Air data into our databases for easier access for our modeling layer. And the modeling layer integrates all these measurements and provides the best estimate of air quality at any given location covered by the model. So on top of this modeling layer, we have a website that provides visualizations. And these visualizations, they contain or consist of a spatial map of estimates with visible sensors and a timeline to compare different locations and sensors. And the final piece of these instruments are the citizens. So they host our AQ sensors, through that support us in collecting air quality data, but they also are the critical consumers of the gathered data. So now Tom will provide you some insights into our AQ sensors.
Hello. My name's Tom. I'm the electrical engineer on this project at the University of Utah. And this device is the AQ pollution monitor. It acts as a single node in our interconnected IoT network. And it's made up of a bunch of different sensors that go into it and contribute to the data point that gets uploaded to our server. The most important sensor on here is the Plantower PMS-3003. It's a low-cost PM sensor. We chose it because it's really reliable and accurate, and it's capable of producing PM1, PM2.5, and PM10 concentrations. And then also, because of the strong correlation between PM measurements and relative humidity in the environment, we also included a temperature and humidity sensor to maintain accuracy in high humidity environments. The device also includes a GPS module, so the user doesn't have to manually enter the physical location of the device, and if it moves around, we'll have some notion of that and we can track that data. And then through our first deployment, we found that since the sensors are located on the exterior of the homes, a lot of them actually have really bad data or internet connections. And so to mitigate the loss of potential data going back to the server, we've included an SD card. And in the event that the monitor does go offline, the SD card will collect data, and when the monitor eventually does go back online, all that data will go from the SD card back onto the server. So you won't lose any of the information. And then the processor we chose to control the functionality of the whole thing was the Texas Instruments CC3200. We chose this chip because it has full Wi-Fi. Oh, I'm sorry, am I not close enough to the mic? Oh, I'm so sorry, guys. No one told me. So we chose the CC3200 because it has full Wi-Fi integration on the chip. So when the user gets their sensor, it's as easy as just connecting it to their home Wi-Fi network. And then it handles everything else. It'll remain connected to the network and reconnect if it becomes disconnected. And then all of this hardware is packaged into this sleek little housing. And it's lightweight, it's really unobtrusive, and it just goes on the outside of the home. And then I should also mention that a great step forward we've taken with these sensors is to calibrate every single PM sensor individually in our laboratory. And then that calibration data is stored on our server. And so raw data points from the PM sensors go online to the server. And at that point, the calibration is applied to them, and users can see the raw data as well as the calibrated data. And so you can see the trade-off and how well the calibrated data is actually adding to the raw data. Oh, I'm sorry. And the way it works is once the device is on the network, it just collects data continuously, and every minute it uploads a data sample to the server, and that's stored in an online database. And through our open API that Pascal develops, you have complete access to all that information. So this sensor is our second generation. It's come a really long way from our first generation sensor, but ultimately we'd like to get all of this technology into a wearable device. And with wearables, the benefit here is that we can reduce the price point significantly, and we can ultimately get a lot more of them out into the community and collecting data. But unfortunately, because of a device of this size, it's hard to squeeze all that functionality into the chip. So we really have to rethink the design of the sensor, and that starts with the redesign of the PM sensor. So just in case anyone doesn't know how low-cost PM sensors work right now, they use a principle called light scattering. Basically, PM goes through a chamber. You can see a diagram of this picture on the left. PM goes through that chamber and past a laser, As light reflects off of the laser, it comes and gets absorbed by a photodetector, and we turn that measurement into a PM concentration. And then the diagram on the right is just a representation of the PM sensors we use right now. They make use of that light scattering technique. And it's really good and it's an accurate technique, but unfortunately it takes a lot of space and power to operate correctly. So integrating this type of sensor into a wearable device just isn't a feasible option. So instead, we're designing our own PM sensor. It's completely passive, and it'll be about 95% smaller than the current optical sensors. And it can be integrated directly onto the PCB, which is a big plus. The technique with these is that we're ultimately going to have a microscopic array of electrodes that are electrically charged, and when you pass particles over this electrode array, or you deposit them directly onto it, they'll disrupt the electric field, and this is something that we can measure and then quantify and turn into a PM measurement. So ultimately with this design, we're sacrificing some of that accuracy and speed you get from the optical solution in lieu of smaller, more energy efficient, and a much cheaper sensor that we can turn into a wearable device. So what that means is that once we have all these sensors fabricated, we've opened the gates to a whole new method for pollution monitoring. These wearable sensors will allow us to fill in all these inevitable gaps that are left by our current generation of sensors. This map is our current deployment in the valley. We have about 50 sensors up and running right now. And you can see on the east end of the freeway, on the east side of the valley, we have a really good concentration of sensors. But west of the freeway, we don't have a lot of hosts, and so we don't have a lot of data over there. And to help mitigate this with wearables, we can have the hosts wear the sensors around throughout the day, and as they go about their travels, they'll ultimately contribute a much denser data set, and we'll get a better spatial resolution out of it. So it's true that we do lose a degree of accuracy with the wearables, but the amount of data we collect will be so dense that we can apply these really precise correction algorithms to that data. So really we won't lose much accuracy as opposed to the current generation of sensors. And with that, I'm going to turn the time back over to Pascal so he can tell you more about the visualization of this data we collect.
Thank you, Tom. So because we are using these low-cost sensors and our goal is to make them cheaper and smaller, we will get even less accurate data. So we will end up with a database full of measurements, each with their own strengths and weaknesses. To mitigate that, we calibrate each sensor before sending it out. And we use a statistical modeling layer between the database and the visualizations. So for the modeling, we are using a method called Gaussian process that takes a set of measurements over a geographical area before and after the point of estimation. And basically what we do is aggregate data from different sensors in time and space, and this results into a model that we can query for estimates at any given time or location covered by the model. So in addition, this model provides us with a measure of uncertainty for that location. And to be clear, we do estimation, but not prediction. So the spatial map of estimates provides the best estimate at that time, at that location, based on the available sensor data. And we are currently working on including land use and elevation into the model. So this is what we currently have, and what we propose is a map of estimates. The citizen can click anywhere on the map and get the best possible air quality estimate at that location. Also, it will populate the line graph at the bottom with the model estimates over time. I removed the timeline to have here a better view of the estimate map. So, and what you should hopefully see is that in the avenues, which is at elevation, is green, and the air is pretty good. So whereas in downtown Salt Lake City, it goes toward orange and red. So this model is also a tool to understand where we need more sensors and if the sensors are at the right locations. So for example, everything that is to the left of I-80, left on the map here, is clearly underrepresented in terms of sensors. So this map of estimates is still very much a work in progress and not yet publicly available on our website. So initial feedback from our sensor holding citizens concerning our visualization without the modeling layer and only showing the sensors have been interesting. For example, The citizens here said, I've been watching the sensors and have been a little bit skeptical of the reported values. In particular, I wonder about calibration, sensor noise, temperature stability, and the effect of direct sunlight. Anyways, this morning I noticed a spike into the red zone before 9 a.m. and I realized that I was using the snowblower to clear the driveway at that time. So this is anecdotal, but it did boost my confidence in the measurements. So where do the citizens fit into this project? Without them, this project would not work and be pointless. So we recruited sensor holders over our website, and currently we have around 270 volunteers. So some of them are also willing to pay to get such a sensor, so this shows that citizens are really interested in air quality. So citizens are basically the cornerstone of this project as they host our sensors, but also because they consume the proposed air quality data. So in this presentation, we hope to have given you an overview about the AQ&U instrument. What we are trying to achieve with this project is to provide tools and the necessary infrastructure to empower citizens. So this means starting with having a dense network of sensors over the Salt Lake City Valley. And for us, the future lies in wearables. How can we communicate this gathered data in a scientific but understandable way to our citizens so they can comment, discuss, and debate using air quality data and eventually push for policy changes? So how can we in general engage citizens to talk more about air quality? So to conclude, there is still a lot of work to do to make gathered air quality data useful for the citizens. And with that, we are happy to take any questions. Thank you.